So, I hope I am audible to everybody. Hello to all the beautiful souls present over here. It is so wonderful to see you all every month in the gatherings. With immense pleasure, I welcome those of you who have been with us for a long time now, as well as those who are new to this group. I am Gunjan Malhotra, your host for the event. And as we all know that we all have gathered here for this month's student gathering and the celebration of World Water Day. No, before starting further, let us gear up together to watch a beautiful video, and I'm sure you all are going to like it. Thank you. Auntie, please help to share the video.
All right, can you hear me?
Yes, loud and clear.
Water is the fundamental ingredient for life on Earth. Looking at our Earth from space, with its vast and deep ocean, it appears as though there is an abundance of water for our use. However, only a small portion of Earth's water is accessible for our needs. How much fresh water exists and where it is stored affects us all. Nearly 2/3 of this fresh water is stored in the polar ice caps, snowpacks, and glaciers, making it inaccessible for long periods of time. The water cycle is dynamic. It describes the continuous movement of water on, above, and below the surface of the Earth, and the transitions from one state to another. Sea surface temperature, surface winds, and air temperature influence the rate of evaporation at the ocean surface. In the tropics, warm ocean surface temperatures support high rates of evaporation. Wind also increases evaporation. When the air's temperature is warmer, it can hold more water. While the atmosphere does not store a large quantity of water compared to the ocean, rivers, and lakes, it can transport water quickly from one place to another. Low-lying regions of the atmosphere with high moisture and strong winds can form atmospheric rivers to transport water horizontally. Clouds are formed as water vapor cools and condenses into droplets and ice crystals. Clouds and water vapor act as insulators in the atmosphere. Clouds help shield the Earth from the sun and trap heat from below. When cloud particles grow large enough, they may fall out as rain or snow. Under the right conditions, areas of precipitation can grow into large storms. As storms grow, they transfer heat vertically into the upper atmosphere. The migration of storms helps to distribute heat between the equator and poles, shaping wind patterns globally. How storms grow and intensify depends on atmospheric moisture, surface temperatures, and wind patterns. Precipitation is concentrated in some parts of the world and scarce in others. It can vary substantially from season to season and from year to year. Water that falls on the land surface as precipitation is stored within snowpacks, lakes, reservoirs, soils, and underground aquifers. Water availability varies from place to place and over time. The availability of water affects the type and abundance of vegetation, the primary source of food for animals and people. Extreme water cycle variability, unusually dry or wet conditions, impacts humans worldwide. Each year, hazards such as floods exact a costly economic and human toll. Most of the water that falls onto land remains stored there for weeks or more. Snowfall is stored as snowpack or ice. Meltwater and rainfall are stored in lakes and soils. Some of the water is absorbed by plant roots or drains into the water table. Eventually, the water will evaporate to the atmosphere or return to the ocean in streams and rivers, providing a source of nutrient-rich water that supports ocean life. Sensors on a suite of NASA satellites observe and measure water on land, in the ocean, and in the atmosphere. These measurements are important to understanding the availability and distribution of Earth's water, which is both vital to life and vulnerable to the impacts of climate change and a growing world population.
I hope everyone will agree that it was a nice video. Let us move to our next part, in which we have a special guest with us today, all the way from NASA, to discuss and brief us about the challenges of the deep space. Along with that, how can I forget to introduce our moderator for this event, all the way from Greece? I welcome Adriana Cordero and would like to hand over the screen. Adriana, the screen is all yours.
Hello, good morning. Good morning to all. Good morning to Pakistan, Modern School, to Cuba, and of course, United States, and all the states that are joining here with us. Of course, what is so important for the planet. And we appreciate that we have this organization that is NASA. And I want you to present that it's NASA and it's worry about this situation and worry about our planet and do all the things, all the missions focused to protect our planet. And I want you to present Mr. George Salazar. He's from NASA. He's from Johnson Space Center. Mr. George Salazar is the product of the barrios of Corpus Christi, Texas, where he was born and grew up. He received his Bachelor of Science in Electrical Engineering from the University of Houston and his Master's of Science in Systems Engineering from Southern Methodist University. He has over 38 years of experience in telemetry, communications, speech control, command and data handling, audio, displays and controls, intelligent lighting, project management, and systems engineering, of which he has received various invention patents. He's currently serving at NASA's Johnson Space Center as a human-computer interface technical discipline lead to develop advanced human interfaces to monitor and control spacecraft, as well as serving as a displays and control subsystem manager for the Commercial Crew Program and the Artemis Moon Human Lander System. He is registered professional engineering in the state of Texas. Also, he has expert systems engineer professional certification to the International Council on Systems Engineering. So it's a pleasure to have here Mr. George Salazar. I'm so glad to have you here in this presentation about challenges of deep space, human space flights missions. Thank you, Mr. George. Would you like to share your presentation?
Yes, thank you. Can you hear me okay?
Yes, we can hear. We can hear you.
Okay, good. Hopefully, let's see if I can
Okay,
share my
Auntie.
presentation here.
Auntie, could you allow
And
Mr. George to present to enter his display presentation? This his
can you,
slides.
can,
Yeah.
do you see it?
Yes, we can see you.
I'm sorry, I can't hear. What can you hear? Can you see it?
No, it's not at the screen.
Okay. All right. So,
Auntie, can you give the control to Mr. George Salazar
Already,
to let
already,
him
already.
start the
do you
presentation?
see it? Do you see it now?
No,
I think you share the Zoom screen, sir.
All right. I'm having difficulty picking up the audio. Um, okay. So, do you see the first slide?
No.
no, George.
Okay. All right. So, do you see it now?
Not yet.
Huh. All
Try
right.
to.
That is
Please, Auntie,
interesting.
give him the permission to start the presentation
Already, since the beginning.
or the controls to make him start the presentation that he can share his slides.
Do you see that?
Yes, yes.
It says it started.
You see it?
Sure. Yes.
Okay. All right. So that's in non-presentation mode. Let me see if it goes into presentation mode.
Okay.
Does it go into presentation mode?
No, but you can. We
Yeah,
can
this
see
is the slide.
that presentation slide by the slide. If you have some
Okay, I'm
problems
just.
with the display,
Yeah.
you
All right,
can.
understood. I'll just present from non-presentation mode. All right, so hopefully you see the first slide, the challenges of deep space human spaceflight missions. And so what I want to do is just kind of give you a let's say a high level overview of what is it going to take to go to other planets and live and work on other planets. So my presentation basically is the human experience on another planet and our planned human spaceflight programs that we have going on right now, and then also talk about the challenges and then some concluding remarks. So let's see. All right, let me do it this way. All right, so humans on other planets, we've basically been to the moon. And, believe it or not, even though we had several Apollo missions, altogether, astronauts spent only 80.6 hours on the moon. That's a total of 3.4 days, which is not a lot of time, not a lot of time working, living and working on another planet. Of course, the Apollo space program had a different objective than the Artemis program that we're currently working toward becoming a sustainable moon project, where that we have astronauts living for a long period of time on Earth. So we have a ways to go in learning to live on another planet. 3.4 days is not a whole lot of time. Um, so the next thing I want to talk about is the planned human spaceflight programs. And so, early on, we like, for example, the space station programs and the shuttle programs and all these, we had a very dependency on mission control. So mission control has over 250 people that support space missions in low Earth orbit. As we start going to the moon, we still have that support because it's only about 2 seconds of delay in communications with the moon. And so it's not so bad in communicating from Earth to the moon and talking to the astronauts. And astronauts can still enjoy talking to family and relatives and whatever. As we start going further out, we can no longer depend on mission control. We're going to have to depend only on the astronauts, the spaceship, and all the intelligence that spaceship has. So we're going to go from a what we call crew mission control robotic dependency to more of a crew vehicle robotics dependency. Again, because the long delays in communications with mission control is going to make it almost impossible to deal with, let's say, for example, critical events, a fire on board or loss of pressure and all that. So it's going to be a little bit more challenging because of the time delays. So the Artemis program is going to be a proving ground. And what does that mean? That means that we have to learn how to live on another planet. And obviously, the moon, because it's not too far away, is the perfect proving ground for it. It's a little challenging in terms of the lack of let's say resources there, and that's something we're going to have to learn how to extract, if you will, from the moon, so that way astronauts can live and work on another planet. But what you see here is first the Artemis 1, and that just happened not too long ago. We sent a spacecraft with no people in there other than a mannequin to the moon and stayed there for about 23 days total before coming back to Earth. But then Artemis 2 is going to be the first humans to orbit. They're not going to land on Earth, on the moon. They're going to be in there. They're going to orbit around the moon for about 20, 21 days, and then they're going to come back. And then we're going to have the first solar electric propulsion system that's going to go up as part of the development and buildup of the lunar, I guess we call it the Lunar Space Station, and it's called Gateway. And so the first pressurized module is going to be delivered to Gateway, and now you've got a propulsion system to keep the Gateway orbiting around the lunar moon. And then we're going to have the mission human lander system, and that's something that I'm working on. Is the lander system is going to be let's call it the first taxi, if you will, that's going to take people from the orbiting space station Gateway down to the moon's surface and then bring them back up. The first human lander system is going to be provided by SpaceX. There is another one that's going to be developed later from another vendor, and the reason for that is so that way we have multiple vendors that can take astronauts to and from the Gateway to the ground. And that's going to be Artemis 3. That's going to be a crew mission. Now, down here at the bottom, you can see a lot of structure there. This is the infrastructure that's going to be built over time, not only by commercial partners, but also international partners. we're looking at oh gee, something like 8 or 10 different countries right now. They're going to be developing hardware for the infrastructure, and I'll say more about that later in my next slide, which is coming up here, and that is the path to sustainment. Okay, so what does that mean? That means that now we have to start building the infrastructure more and more, so that way humans can live on another planet. The first slide you see, I mean, the first one right here you see is related to the delivery of the gateway of the in situ resource utilization, which basically is going to be the let's call it the machine that's going to take moon soil and convert it into water so that the astronauts can drink. It's a big challenge because the moon surface, the moon soil, is not it's not very good. It basically, like a friend of mine told me that works on in situ resource utilization, moon dust is kind of like crushed glass, very abrasive. It can basically wear pieces out and stuff like that. So it's not like your regular sand that's very round, and each particle is very round. It's very abrasive. It's got a lot of ridges and a lot of sharp points, if you will. But that's a challenge, is to develop something that can take soil from the moon and create water. And that's going to be obviously very important because we can't take the thousands of gallons of water that the astronauts are going to need, especially when we go to Mars. And then we start getting to sustainment operations, more of lunar communications. We're talking about laser communication, so we can transmit a lot of data over a laser communication network. Right now we have what we call RF, or radio frequency communications, but it's just not enough data to transmit, let's say, for example, video, or other things that requires large amount of data. So that's another challenge. It's in the area of communications. And of course, we start developing, we'll deliver an airlock. So that airlock now provides an opportunity for the gateway to have let's call it a parking garage for different vehicles to come to the gateway and eventually go down to the surface of the moon. And then habitat, habitat is going to be a big thing. We got to have a habitat that not only protects the astronauts from the radiation effects, but also provides a nice living quarters for the astronauts. Now, there's discussions of digging holes underground of the moon, so that way they can protect against radiation. And that's another challenge because we have to have large machinery to dig those holes. And that becomes another problem in terms of delivering large machinery to the moon surface. And also the machinery could break down because of the dealing with the moon soil, the moon's lunar dust, which again, as I said, is quite abrasive. So that's another challenge in itself. Down here at the bottom, you see different extra vehicle activity, people in suits. We have rovers, we have we call power stations. A whole bunch of things are going to have to need to be developed. Again, we're developing an infrastructure, a small community, if you will, that we're going to stay there for a long period of time and learn to live and operate on another planet. Let's see here. So next thing up are the challenges. And the first challenge I'd like to bring up is the human. Okay, the human is not a robot. we're organic material, and we have emotions. We have things that we have to deal with in going to another planet. One of the first challenges is the physiological effects of gravity or the lack of gravity that we're accustomed to. And so we have to balance that with exercise in order to mitigate the effects of being in microgravity, or in this case, a very low gravity on the moon. And of course, low gravity affects the human in terms of dealing with fluid shifts. If you got a cold here on Earth, your sinuses drain, right? Well, if you have a cold in space, your sinuses are not going to drain. They're going to stay in your head. And that's why sometimes you see astronauts' heads look real big because their sinuses are not draining. So they have to take special measures to get rid of that sinus pressure buildup, if you will. Muscular atrophy. Your muscles no longer are working against gravity, and so your muscles start to deteriorate, as well as your bone loss, calcium loss. The body says, "Oh, the gravity is not as bad. I don't have to produce calcium to create strong bones." And that the problem with that is that you have an astronaut that starts to become more brittle. All right, so that's one of the big effects. The other major one is space radiation. Space radiation, it's a tough problem to solve, and of course for the human, a lot of radiation, too much exposure, obviously can create cancer. But there's also what they call cognitive neural system um, uh, uh, depletion. Basically, that says that the radiation is causing issues with your ability to think, your ability to comprehend. These are factors that we have to consider when we're designing instruments that are being used by astronauts that maybe one day they're not feeling well, and they're trying to command and control a spacecraft where they shouldn't be, and that's why autonomous computer systems come into play. The other one is a big one too: isolation and confinement, being away from family. Again, uh, on the moon, it's not going to be as bad. So looking at some of the studies done, psychological studies done with astronauts, as long as they see the Earth, they still feel that tie, if you will, being close to Earth. On space station, I don't know if you've seen this cupola that's got a lot of windows around it, and astronauts just sit there and just look out at the Earth, and it feels like they're tied to it. Well, imagine what happens to the astronauts as they start moving further into space, and now they see Earth as a little tiny dot. They can no longer see it as a big Earth that's close by, and so it can affect them psychologically. Working with another crew is going to be another challenge. Dealing with different, let's say, international partners. Well, everybody has their own. We all have our different cultures. We all have our different beliefs. We all have our different ways of seeing things, and so uh, that interaction is going to be real important when they get further away, because they're going to have to depend on each other, and if they can't get along, it's going to be it's going to be a long flight. Dealing with that. So the isolation and confinement is a major challenge that we still don't have quite an answer to that. And then, of course, it's a hostile environment. You add hostile environment to isolation and confinement, it can make a person, even astronauts. Astronauts are human. They're not super people, and so you have a situation where you're far away from home, you're constantly at risk of losing your life because of where you're located, and so it plays a number on your brain, if you will. And then, of course, we have to grow food, we have to grow water, and as we start going further and further away from Earth, we cannot depend on a resupply of food that comes right away. It's going to be dependent on where the Earth and Mars are, It could be 9 months before they get their next resupply. During that time, they need somewhere in the vicinity of thousands of pounds of food and thousands of gallons or liters of water in order to survive for that long period of time. So how are we going to do that? And that's a challenge. Um, the whole area of medical is also a major challenge. What happens if an astronaut gets an appendicitis? And you say, well, I thought appendicitis has only happened to teenagers, and no, it happens to adults. A colleague of mine, he got an appendicitis attack not too long ago, and he didn't expect that. He thought he had an upset stomach. So we have to be able to deal with that, and of course, things like heart conditions, lung conditions, major trauma to the body. How are we going to operate on somebody that has a big cut that they experience from something happened during one of their missions? So these are the things that we have to deal with as we start going further into Earth. So I just got through talking about the let's call it the human aspect of it. So there's also now the technology aspects of it. And I'll just kind of briefly go through these. The first one is uninterrupted power. We're going to need a lot of power and for a long period of time as we go deeper into space. We talk about nuclear energy and things like that, but there's pros and cons for using nuclear power. One of them is you got to protect the astronauts from the radiation effects of a nuclear power source. And not to mention, if something goes wrong with that nuclear power station, it could create radiation effects that could kill astronauts. We're going to have powerful propulsion systems, to take us to Mars very quickly. The shorter the time it takes the astronauts to get to Mars, the shorter the exposure to the big radiation effects. Radiation tolerant electronics. These electronics have to work in space for a long period of time. Radiation is a big factor in the electronics operating for a long period of time. And they're not cheap. Building electronics to deal in the radiation environment can be quite expensive. Extra vehicle Activia spacesuits. Right there, you see a picture of the Axiom spacesuit that was just shown on internet, and it's a really nice spacesuit, and it's not as bulky as the one that they use on Apollo. Still, there's a likelihood, a possibility that a micrometeorite could hit that spacesuit and puncture a hole in it, and they start losing pressure and they start losing oxygen. So that's a challenge. Deep space habitat. The habitats, as I mentioned, we're going to have to build them not only to protect the astronauts from the external environment, but also they can live and work in a very nice environment, if you will. Deep space communications too, as I mentioned, things like laser communications. We start getting further away from Earth. We would like to continue having conversations with family loved ones, and we gotta have something that's high speed, and lasers is one way of doing that. Entry descent systems. This is basically how we're going to land very large structures on another planet like Mars. Mars Science Laboratory, the Mars 2020 robot, they weighed about 2,000 pounds. That's the maximum amount of weight that we can land something like that on another planet without coming up with some new way of landing it. So it's a major challenge as something gets bigger and heavier. It's talk about science. It's the kinetic energy to try to slow something down that big going into the Earth's into the Mars atmosphere. So it's a major challenge there. And I just mentioned about medical systems, and then I think I mentioned about institute resource utilization. That's going to be important for future space missions. And so, one of the mission challenges is dealing with risk and hazards. And I always like using the James Reason human error model, it basically tells you why sometimes accidents happen. And so, if you think about barriers as things that are we use to protect against faulty equipment, it's we call it the Swiss cheese model because each one of these, this is circular cheese and not square cheese, but basically these barriers, like for example, design, you're trying to design against the environment, but our designs are not perfect, and we got holes in them, and that's what those holes represent. That they represent imperfections in that barrier. And so all these pieces of cheese, if you will, the holes, are rotating over time. And there's an event or a hazard that can happen. Like, for example, you flip the wrong switch at the wrong time. And things just line up perfectly. We forgot to do a requirement for this. We forgot to design for that. We didn't test for that situation. We didn't look at a review. Our human factors engineers didn't look at that piece from the human, and so things line up where an event can go right through all the holes and create a hazard or a consequence. Okay, and that's I really enjoy this or strongly believe in this because a hazard or a catastrophic event is not because of one thing, it's because of multiple things that happen at the same time, and everything just lined up perfect for that particular day, that particular hour, that particular minute, that particular second, that it just caused a avalanche, if you will, of a problem. So what do? We one of the things that we do try to reduce the number of holes, if you will, like for example in the design of systems, is do a lot of testing. So right here you see a model, or actually it's a graphical representation of what we call the failure bathtub curve of hardware, like for example electronic components and mechanical systems. And so early on, it's called the burn-in phase. But during the burn-in phase is what we call infant mortality. In other words, these parts are new, and they may have been produced incorrectly, and they fail early. If you test them long enough, now we have something called the constant failure rate, where we can predict when things are going to fail because we know so much about the failure rate of this component, we can predict it. And then as parts get older, uh, like humans, we start wearing out and parts start failing, and so you have to plan for end of life of your components. You don't want to get to this point. You want to replace something that's going to wear out before it gets bad. And so right here you're seeing different kinds of testing that we do based on the space environment. Over here you see thermal testing. You see electromagnetic testing to see if one part doesn't interfere with another part in electromagnetics. Vibration, we test for the vibration and shock as well. And then we test for radiation. Radiation testing is very expensive. Giving an example, to test a circuit board at Brookhaven in New Jersey in the United States, if you test that board for about 3 days, it's going to run you about $60,000, $70,000 US dollars. And then so we also have safety hazards and hazard analysis of the design. We do those constantly throughout the life of the project because we will try to uncover, again going back to the Swiss cheese model, we uncovered holes that we overlooked, and the more we look at it, the more that we'll say, oh, this design does not have that. Oh, we overlooked this in the design. So it's a constant what we call iteration of looking at that equipment. And for the hardware, the same thing for software. Software has a different failure rate than hardware. Software has no moving parts, right? But when you code software, you create a lot of errors, and you have to find what those errors are. And so you see these slopes right here. These slopes is where you're finding the bugs and errors. You do an upgrade, you do a let's call it a software rewrite of some sort, but you create errors, and then you find those errors, and then you do another upgrade, you create errors, and you find those errors, and you bring them down to eventually you find all the errors. And so we do a lot of testing down here. Is kind of representative of some of the software testing that we do. We have use cases, we have requirements, we create a design of all these use cases and requirements. We code it, whether it's in C, C++, Python, or whatever language, and then we test. We test at different levels, at the unit level, the small level. We test different pieces together. We stress test it to see how much can this software handle in the hardware environment before it starts to break down. And then we do systems testing where we test all the components together and see how the whole system works. We evaluate, we go back and do it all over again if we have to. Again, we're trying to find those holes in that piece of cheese so that way we get rid of problems that can occur. Again, just like hardware, we do safety analysis of the software, hazard analysis of the software, and try to refine the design and try to get rid of those holes, if you will. And then for the human, it's the human-centered testing. We constantly are trying to deal with the task. What does the astronaut have to do? And then what is the hardware and software needed to do that task? And what does the human have to do with that? And so we're constantly trying to match the task to the hardware and software that's needed to do that task. We're also trying to match the human to the task. Some tasks cannot be done by humans. They have to be done by machines. And then you have to match the human to the hardware and the software to see if they work properly. So in a Venn diagram, we can optimize our design by iterating through this whole process. And we're trying to minimize human error. We have the humans have different ways of causing an error in a system. Sometimes there's skill-based human errors. So skill-based human error is like, for example, I know how this system works, but on that particular day, on that particular minute, I forgot how to do that, and I hit the wrong button. And then there's the what we call the mistakes, and these mistakes sometimes happen because it's a totally new system and it's not what we're familiar with. We're familiar with this way, and now we got this new system, and I made a mistake because I was thinking that it operated like the old system, and it doesn't. So you make those kind of mistakes. And so those are the things that we do when we're testing to make sure that the astronaut is using, the astronaut has the right tools, has the right systems in place to perform the task. Let's see here. So collectively, the total system development is a combination of doing the systems engineering process, developing requirements, developing technical solutions, developing systems development, integration and testing. In parallel with that is you got the human stuff going on in terms of understanding the user and the environment, understanding the product solution that's going to help the astronaut solve the task or work the task, and then evaluate the design against the human. And if there's shortcomings, then they iterate again. If you look at it collectively, as I mentioned earlier, we're trying to optimize the design for the human in the task. And we do things like workload analysis. In other words, how much work is it going to take for the astronaut to do this task? Usability. How well can this be used by an astronaut? Is it too complicated? Uh, do they tend to make a lot of mistakes because the user interface is very complicated? And these are the things that we keep iterating over again. These are going to be vital. Obviously, the analysis is going to be important too. These are the things that collectively we as NASA with the international partners are going to be doing quite a bit of as we start pursuing the Artemis program, where we're going to live and operate in space. The thing is, once we launch, it's going to be very difficult to make corrections. We try to do it. We try to make those corrections early on and not after the fact. So that's the challenge, is having a process in place for not just the hardware, the software, and the human, but also how do we refine the design to make sure we get rid of those. Again, going back to the Swiss cheese model, how do we get rid of a lot of those holes in that Swiss cheese? Is the bottom line. So, in short, in conclusion, going to the moon, we're going to learn to live on another planet. That's what the Moon Artemis program is all about. And it's got to be a catalyst for technical innovation. I can say that there's a lot of things that we need to invent before we go to Mars. Commercialization. There's going to be commercial partners that are probably going to get involved with the moon exploration. I'm certainly. I was in a conference the other day, and there were a lot of commercial companies in space, and they're very interested in going to moon. However, commercialization, they have to weigh the risk against profit, right? Because they have to satisfy their shareholders that invest money in that company. So these are some of the things that they're going to be occurring near term. And later, maybe in another 10, 15 years, is moving on to going to Mars. And that's going to be a big challenge. And of course, for Mars is search for life. Already Mars 2020 and Mars Science Laboratory robots are already showing indications that there was water on Earth, on Mars, potentially organic life could occur there. So but the human is much better at analyzing than some of the instruments that we have built over time. And then space settlement. Basically now we know how to settle on another planet. Think about the early frontiers of the Western days here in the United States, for example, and maybe other countries where people came from other countries and landed on the shores of a new world, and they learned to explore. They learned to live off the land and all that. But of course, being on Earth is far different than being on the moon and Mars, where there's no plants and animals that you can take advantage of in terms of food and water. But these are the challenges that we have. And certainly I think we'll overcome them, with the help of the commercial partners, international partners, students, everybody else coming in and helping out, to make this a successful project. So that basically was my last chart. And so now I can open up for questions. And my preference, if you can, because I was hearing the audio being a little distorted. If you can type in the questions, and I'll try to answer as many. I do have to drop off in 13 minutes because I got to get ready for another meeting. So
Okay.
with that.
Okay, George. Well, thank you very much, George. Your presentations are always very interesting, and you have a great labor as a leader in the human-computer interface. The challenges that you have mentioned are a big area, a big opportunity for all these new generations that are interested in NASA. Okay, but I'm concerned, very, very concerned about the moon soil that you have mentioned that we need to transform to water. I'm very concerned about it. But let's start to do the question and answer time. Let's go ahead with the questions. Okay, and let's see. If you have some question, please pick your hand. You pick your hands up or write it. Write it. I will tell to Mr. George Salazar if you have some questions. Do you know, George, if you are walking or has the future program for this moon soil transformation into water?
I'm
That you
sorry,
have-
can you repeat? What about?
if you know about some program about this moon soil transformation into water.
Yeah, I mean, we're looking at this in situ resource utilization at the Johnson Space Center in Houston. We have a group that's developing the machine, if you will, for converting moon soil and Mars soil into water. But it's not easy. I'll give you an example. The gentleman that showed me the machine, he showed me about maybe a little small cup of water, very small amount of water, and he said it took him almost something like 8 pounds of soil to get that little bit of water, and that there were a couple of things. One was you don't get a lot of water out of a lot of soil. Secondly, it did not smell very good. I would not drink the water. We're still learning how to make that water better. So
Yeah.
it's and I'm sure commercial companies are going to be interested in it, because if you think about it, there's something called dual use technology. In other words, you can use the technology in two places. One is in space, okay, like for example, in situ resource utilization, but also think about how we could use that here on Earth. Let's say, for example, in Africa, where they live in the desert, and they could put desert sand into this machine and produce water. So it's dual use. You can use it in space,
Yeah.
and you can use it here on the Earth, and so that's
Yeah.
something that we're looking at.
That-
I see it.
That's very interesting. We have some question.
Yeah.
George, sir, when will be a teletransportation machine be made? Till which year? Do you know this, Mr. George? Or have you heard something about this teleportation machine that you mentioned?
Yeah. So yeah, I imagine this person watches Star Trek. Uh, it's they're doing that right now, but it's there's a lot of challenges to teleporting somebody over. If you think about what teleportation is all about, it's basically break you down into your molecular structure and recreate it somewhere else. Well, there's something called, and maybe some of y'all are familiar with the Heisenberg uncertainty principle, that basically says we don't know exactly where this particle is in time, but here's the likelihood where that particle is. So if you think about transporting a particle, you're not sure if you captured the right particle or not and transported it to the right location. So uh, taking something apart and then building it back up, there could be some challenges. You may not build it back up properly. So we have a long way to go. I know eventually we will. I mean, so far, the only thing they've ever been able to prove is teleporting one proton, maybe about 15 feet, if I recall correctly. But to do that for a human or anything else, we got a long way to go. So maybe somebody in
Yeah.
the audience there will create that. But for now, it's a long ways off.
It's, yeah, they need a lot of research, and I think they are doing at the CERN with all the particles. Okay, if there's some question, any question here? Any question here? No? Well, thank you very much, Mr. George Salazar. Thanks for your presentation. Again, I'm so glad to have you here. It's a pleasure, and thanks for your friendship also. Thank you very much. And I'm going to tell Gunjan to start again with the water presentation or to the close up. Thank you
All
very
right.
much. Thank you all, and to all
My
the
pleasure.
countries that are joining
Bye-bye.
here. Bye-bye.
Okay, so I would like to express my heartfelt gratitude to Mr. George for this insightful session and Andriana for making it a perfect one. Thank you so much. Now we will be moving to the next part of the session. Water is the driving force of all nature. And I believe that we should all be like water, formless and shapeless. Because if we put water into a cup, it becomes the cup. And if we put water into a bottle, it becomes the bottle. Similarly, we all are here together on this platform today to learn, share, and grow together. And here we are with some of the good practices which we follow in our own ways to save water. So here comes the first video all the way from a country which boasts a myriad of gorgeous islands and beaches. Yes, it's Indonesia. I would like to appreciate the sincere efforts of the students of SD National KPS Balikpapan, led by teacher Auntie. Auntie, please share the video.
Science team of SMA Nasional KPS Balikpapan, Indonesia, and today we're going to show you a video to celebrate World Water Day.
My name is Nelson. My name is Christian. My name is Diego.
I'm Celia. I'm Atifa. My name is Nayara. My name is Almira. My name is Lily.
My name is also Irfan. My name is Chris. And my name is Andrea.
Enjoy the video!
Water. Is it important for our life? What does it mean for us? Do we even know its true value?
Humans, animals, and plants all need water. Let's see how water plays the most role in our life. Without water, no food can be produced. No water equals no food.
About 71% of the Earth's surface is covered by water, and the ocean holds about 96.5% of the Earth's water. In fact, only 2.5% of Earth's water is fresh water.
And 2/3 of that is tucked away in frozen glaciers or otherwise unavailable for our use. As a result, some 1.1 billion people worldwide lack access to water, and a total of 2.7 billion find water scarce for at least 1 month of the year.
To imagine one day without water, then what happens if there is a water problem, like water scarcity? So when we face water problem, it is not just about water.
There is a problem of life. It's a problem of health. It's a problem of environment. According to the World Health Organization, around 2 billion people in this world consume water that is contaminated.
The World Health Organization estimated 80% of diseases worldwide are waterborne.
Moreover, around 3.1% of deaths in the world are due to unhygienic and poor quality of water.
This is a global problem that we should all take action to resolve. That's why we have to protect the water. If we don't start now, so when? Do we have to wait until we face the water crisis? Or you just don't care about it? Let's rethink it again and again. How water can help us to survive in our life. Water is essential to life. Water is everything. Save water, save your life.
Wow. Great effort by the high school students of SMA National KPS. That was really lovely. It's time to watch the next video, which has come all the way from the country with unity in diversity, our beautiful India. I would like to appreciate the efforts put in by Mr. Bhola and the students from primary school area. Let us watch the video.
जल हमारे जीवन के लिए बहुत आवश्यक है। जल के बिना जीना संभव नहीं है।
तालाबों, नदियों एवं कुएं के जल को दूषित न करें। इसमें कचरा न फेंकें, इससे जल बर्बाद होता है। जल के बिना रहना न केवल हमारे लिए बल्कि किसी भी जीवधारी के लिए असंभव है। सेव वाटर। पानी की बोतल में बचे हुए जल को फेंकने के बजाय उसे पौधे में डाल दें। पानी बचाएं।
जल है तो कल है।
हम प्रतिदिन किसी न किसी कार्य में जल का प्रयोग करते हैं, जैसे पानी पीने, खाना बनाने, कपड़े धोने में। सेव वाटर।
Wow, it was indeed very beautiful. Next, we have a video from a country which is famous for its traditional northern landscape and rice terraces. I humbly appreciate the efforts of teacher Rosie and her students from Yandang No. 1 School, Vietnam. Let us see the video.
Water in school. Plants. Animals. Students. Water is part of school.
World Water Day.
Yên Dũng High School No. 1 is well-respected educational institution located in Yên Dũng, Bắc Giang, Vietnam. Our school has a long-standing reputation for delivering high-quality education. Besides preserving the natural resources, it also one of the school motto, educating, especially water conservation. Here are some suggested ways that we can save water at school.
First, talk to others about water. Raise awareness of the importance of water by creating colorful posters on water use and water saving. You can even start your own water saving team. Second, if not using tap, turn it off. Turn the tap off as soon as you have washed your hands. Put signs near the basins to remind students to do the same. Finally, check your toilets for leaks. Put a few drops of food coloring in your toilet tank. If without flushing the coloring begins to appear in the bowl, you have a leak that may be washing more than 100 gallons of water a day.
Take care of clean water is also a way to save water. So, do not throw trash near water source. Clean area with water source. It also about to check the purity of the water monthly.
In conclusion, water conservation should be priority not only at school but also in present world. Together we can make this planet a better place because because countless more actions made by countless individuals can be lead to big changes in the environment and for our communication. Clean water is really rare, so never waste even a drop of water.
It was marvelous. Next, we have a video from Nagaland, India by Dr. Carolyn and her students from SIETIIE, Innovation and Research Center. Let us watch that video.
Greetings everyone, this is Razulay Caroline Soreno, currently working as the National Coordinator and National Media Coordinator, the City Innovation and Research Organization, also a soft skill trainer and a professional phonetician. I am sharing some of the practices done in here to conserve water. I hope we all get to find ways and more ideas on how to save water.
Hello, I am Margaret Walne from Teminu village, Nagaland, the northeastern part of India. This is a water reservoir tank. We reserve water during the rainy season so that we could use it during the dry season because there is scarcity of water here.
Hello, my name is Bihij Kakin of Teminu village, Nagaland. This dirty water is from washing clothes. I'm gonna reuse this water to clean the drainage.
Hello, Madhakin of the Manila Village, Nagaland.
This water was used for cleaning rice. Now I will use this one for watering the plants. We do this method of conserving the water because there is scarcity of water.
Hello, my name is Tatangshila Ozukum from Nagaland, the northeastern part of India. After the laundry water, I reuse water by flushing the water into the toilet. This is how I conserve water at home.
Wow, definitely these practices are worth learning. It's time to see a video from a country which is famous for its ancient philosophers like Plato and Aristotle. I would like to thank and appreciate the efforts put in by teacher Helen and her students from 9th Primary School, Greece. Let us watch the video.
Don't waste water.
Water in school.
It was a beautiful one. Now, let us talk about a country with rich amalgamation of African, Spanish, and Caribbean pastimes, food, religion, and of course, dance and music. I extend my heartfelt gratitude to Mr. Fernando and his students all the way from Cuba for their efforts. Let us see that video.
DJ Montesa.
ആ വാഷ് ബേസിലെ വായ കഴുകി കുലിക്കൊഴിഞ്ഞ് ഇവിടെ വന്നു.
Wow, it was so melodious and insightful. Last but not the least, we have our last video, which we have received from definitely my school, and that is Animal Kerala Public School, Jamshedpur. Let us see that video.
It's time to go home, but this bottle is so heavy. Let's go and enjoy it.
Wait, stop, stop, stop. What you people are doing here? Don't you know water is so precious? Can you imagine a life without water? Come, let me tell you how to save and use this water in this bottle.
Hey, what you all are doing? Why are you wasting the water? We need to wash our dirty hands after lunch. But do you know you are contaminating the taps with your dirty hands and you are wasting the water as well because you are not turning off the taps. But don't worry, I will show you how to wash your hands without wasting the water. My dear friends, see how Saraswati will wash her hand without wasting the water using this tippy tap. In this way, you can save water without wasting it. So save water, save life! Hello, Bratin. Hey, Jasmeet. See what I have made. What's this? This is another way by which we can save water. How? Can you please explain? Sure. I have made a self-watering plant using an old potable water, creating best out of best. That's great. But how you're going to save water by this? Yeah, I am telling you. See, by using this technique, I have used a sponge so that the water gets as much water it is required.
So I would like to appreciate the sincere effort of the students of Animal Kerala Public School for this beautiful video. Now, there was one more video which was left all the way from the beautiful country, Argentina. I would like to appreciate the sincere efforts of Marcela and her students. Let us see the video.
Argentina is a large country with strong climate variability. The country extends longitudinally over 3,700 kilometers, and the continental portion of the territory is about 2,800,000 square kilometers, around 5 times the size of Spain. The great latitudinal extension between 22 degrees and 55 degrees south latitude creates wide climate variety from subtropical climates in the northern part of the country to the very cold weather in Patagonia. However, there is a predominance of mild climate in most of the country. When considering climatic and hydrological conditions, 3 regions can be identified in Argentina. A humid region in the northeast, littoral and the Pampa Húmeda region. This receives more than 800 millimeters of precipitation a year and occupies an area of 665,000 square kilometers, It concentrates 70% of the national population and 80% of agricultural production, and 85% of industrial activity. A semi-arid region, central strip of the country, which concentrates 28% of the national population, and irrigation is essential here for the development of certain crops, given the important water deficit during a large part of the year. And an arid region, most of the northwest and central west of the country, that concentrates only 6% of the population, and agricultural production is completely dependent on irrigation. Argentina is a water-rich country with an even distribution of water resources. Renewable resources in Argentina, accounting for long-term averages, are approximately 20,400 cubic meters per capita, which is above most countries and well above the water stress threshold defined by the United Nations Development Programme. The most important rivers in Argentina are those that drain into the Atlantic Ocean, approximately 10% of total national resources, as they act as fluvial corridors of great economic and ecological importance. In 2003, the 23 provinces and the city of Buenos Aires and the national government signed a federal water agreement that laid down the foundations of a national water policy. Through the agreement, the parties adopted 49 guiding principles for water policy, which acknowledge the value of water as a social and environmental resource for the society. The principles call for the protection of the resource. But although there has been some progress, there are still some challenges that remain. They include, among others, interjurisdictional conflicts over waters. Planning focuses mainly on the delivery of hard infrastructure, or discretionary investments carried out with no evidence-based decision support system. So today, on Water Day, let's raise awareness on its importance and remember that it's an invaluable source for life. World Water Day.
Wow. Wow, that was indeed wonderful. So here comes the end of this beautiful show. I sincerely appreciate your attention today throughout this event. I would also like to extend my heartfelt gratitude to Andriana for being there with us till the end. Now, I would like to conclude this event by being a representative of Global Teachers Club, and let us meet again for the next session. So it's time to bid a goodbye for now with a promise to meet up again in the next gathering. So here comes the goodbye session. So see you all in the next session. I hope everyone enjoyed to the fullest. So let us give a great smile on your faces so that I can click some beautiful pictures of everybody. Okay, lovely. Really, it's so good to see everybody across the globe. It's really marvelous. Thank you so much. Thank you so much, everybody. So let us bid goodbye to each other, and we will meet again in the next gathering. Bye-bye. See you all.
Goodbye.
Goodbye.
Goodbye.